Hi, my name is Asim and I will be presenting the work GrOVe, the ownership verification of graph neural networks using embeddings. Graph neural networks, or GNNs, are the current state-of-the-art for real-world graph-based applications. Many companies such as Twitter or Facebook use them to model their social graphs. However, prior work has shown that model extraction is possible on GNNs, and thus there is a need for ownership demonstration. First, let's talk a little bit about how GNNs work. The main idea is that a GNN aggregates information about a target node from the neighboring nodes as well. So it takes the node features and the graph structure and outputs a single vector that is the embedding of that node. Thus, given an entire graph, a GNN can generate many embeddings, each embedding corresponding to a single node, which can then be passed into any multi-layer perceptron or neural network to do many different tasks. Usually it is trained using a node classification task, however it may be graph classification as well, and then during inference time, those embeddings can be used for classification, visualization, recommendations, and many other tasks. Now that we know how GNNs work, let's talk a little bit about how model extraction attacks work. In general, the idea is that the adversary has access to a target model that somebody else has trained, usually through a prediction API, and the adversary might have their own dataset. And in order to extract the model, the general idea is pretty simple. You send some input, it might be some special input to the target model, and then you use the output from that target model to train your own surrogate model. It turns out that the surrogate model performs just as well as the target model in most cases, even though it is much cheaper than training an entire model from scratch. Recently, Shen et al. Have shown that model extraction attacks are also possible on GNNs, specifically inductive GNNs, and they showed two different types of attacks. In type 1 attack, the adversary has access to both the adjacency matrix, which contains the information about the edges in a graph, as well as the node features, and directly trains the surrogate model. In another type of attack, the adversary does not have the adjacency matrix and instead estimates that before training the surrogate model. However, in both cases, the adversary wants high accuracy on the primary task as well as high fidelity between the target and surrogate model, which means the behavior of the target and surrogate model should be similar. Now, because we know that each input graph generates unique embeddings and we show that the attack's goal is to have high fidelity, we intuit that embeddings from surrogate and target models are going to be similar. In which case we ask the question, can GNN embeddings be used as a fingerprint? Thus, we run a preliminary experiment in which we train many different target models as well as independent models which are exactly the same as the target model but trained independently with a different random seed, as well as some surrogate models. We find that when we visualize the embeddings using a TSNE visualization, the embeddings of the surrogate model fully overlap with the target model while the independent model forms a different cluster. Before we conduct any formal experimentation, we list the desiderata of any ownership verification scheme. The first is that it should be effective, i.e. it should differentiate between surrogate and independently trained models. Secondly, it should be efficient, that there should be a reasonable computational overhead. Thirdly, it should be non-invasive, i.e. it does not degrade the model accuracy. This is true for all fingerprinting schemes. Lastly, it should be robust, i.e. it should resist attempts at circumventing ownership verification, such as compression and fine-tuning. In terms of the threat model, for the adversary we use the same attack assumptions as the original paper, i.e. that the adversary has access to the GNN output, i.e. the node embeddings used to train the surrogate model, and as far as the surrogate and target models training dataset is confirmed, the overlap between the datasets may range from none to full. However, for our experimentations, we only focus on full overlap because that is the most difficult case to solve. For our ownership verification scheme, we also keep it black box. i.e. that the verifier can sample a verification dataset from the same distribution as the target model data, but they need not have access to the exact data as the target model. And secondly, that the verifier can access the target model and suspect model via prediction APIs. We define four stakeholders in our work. The first is the model owner. This is just somebody that trains a model and deploys it as a service. The second is the adversarial responder. This is someone that steals a model from the model owner and wants to evade detection. The third is the adversarial accuser. This is somebody who may or may not even have their own model, but when somebody else trains an independent model, they want to make false accusations against them and claim that they stole their model even though they did not. And the last is a third-party verifier. This is a trusted third party that verifies whether one model is stolen from another. To help the verifier, we define the concept of model registration. And the goal of this is to ensure that the verifier knows which model was trained first. In order to facilitate this, every model owner, once they train a model and deploy it, must generate a cryptographic commitment C of their model such that C should change if the model changes. This can be done by a simple cryptographic hash function. And secondly, they must obtain a secure timestamp of C and then give this to the verifier. The first step in the verification process is that the accuser claims that the responder stole their model, in which case the verifier first checks that the target model, which is the accuser's model, and the suspect model, which is the responder's model, are consistent with the registered models. It then checks the secure timestamps to ensure that the target model was indeed trained before the suspect model, and then samples a verification dataset from the same distribution as the target model data. Because the verifier is sampling the verification dataset themselves and by checking the timestamps, this avoids the possibilities of false accusations. The last step in the process is that the verifier will query the target and suspect models and pass the outputs to a verification algorithm which will give a binary output on whether the suspect model was truly stolen or not. Now that we know how the general verification process works, let's dive a little deep into the verification algorithm that we propose. The key idea is that we want to classify whether a pair of embeddings are close or far, and to that end we train a similarity classifier. The key idea is that we train three models: a target GNN, a surrogate GNN of the target GNN, and an independently trained GNN with a different random seed. And what we do then is that we generate embeddings from all three GNNs. We calculate a distance vector between the surrogate GNN embeddings and the target GNN embeddings, which form our positive samples. We also generate the distance vector between the target GNN and the independent GNN embeddings, which then form our negative samples. Now that we know how to train our similarity classifier, let's see how it's used in our proposed verification algorithm. We start with a verification testing graph which contains many nodes which are passed to the suspect GNN and the target GNN, which then output multiple embeddings. We can then calculate a distance vector between each pair of embedding and pass it to the similarity classifier. As an output, we will get a vector of ones or zeros, where 1 is that the embeddings were too close and 0 is that the embeddings were too far. If a particular proportion of embeddings are closer than a threshold that we set, then we say that the model was indeed a surrogate model. Otherwise, we say that this is an independent model. In our work, we just set the threshold to be 0.5. We found that we did not need to optimize it at all. In terms of testing this entire scheme, we have the following experimental setup. The metrics that we use is firstly the surrogate model accuracy. It should be on par with the target model to ensure that the surrogate model is a true surrogate model. The second thing we check is the false positive rate, which is the proportion of independent models which were misclassified as surrogate models. The third thing is the false negative rate, which is the proportion of surrogate models which were misclassified as independent models. To train the similarity classifier, we only use the type 1 model extraction attack for positive data points, and we use independent models for negative data points. And then to test the similarity classifier, we train additional independent and surrogate models using different random initializations. When we ran the experiment, we found that the GrOVe is effective at verifying ownership, such that it achieved a zero false negative rate for both type 1 and type 2 attacks, even though it was not trained on type 2 attacks. And for Amazon and ACM datasets, the false positive rate was only 2.2 and 3.4% respectively. For all other datasets, we were able to achieve a zero false positive rate. This fulfills the first criteria, but we also talked about robustness, in which case the adversary can post-process the surrogate models to evade detection. Some possible post-processing techniques are double extraction, which we will talk about later, pruning, and fine-tuning. Double extraction is when the adversary runs a model extraction attack against the target model to get an intermediate model, and then runs another model extraction attack against the intermediate model to get the surrogate model. The intuition is that this extra layer of knowledge distillation might change the output distribution, potentially evading GrOVe. However, when we ran the experiment with double extraction, we found that GrOVe still achieved a false negative rate of 0 across all datasets. In fact, on the other hand, for the Amazon and CiteSeer datasets, the surrogate accuracy dropped by more than 6%. So not only is this a less potent attack, but it is also still effectively caught by GrOVe. Now, the idea of pruning is that you may randomly remove some model weights, i.e. set them to 0, and the amount of weights that you remove is controlled by a prune ratio, which is the ratio of weights that are removed. The primary aim of pruning is to reduce model complexity while maintaining model utility, essentially model compression. Secondarily, small amounts of pruning might actually increase model generalization as well, similar to using dropouts. Now, why do we think it would work for evasion? Well, the idea is similar to double extraction, which is that it might change the model's output distribution. We tested GrOVe against multiple prune ratios shown here on this graph on the x-axis. The dotted lines show the accuracy of the surrogate model, while the solid lines show the false negative rate of GrOVe when tested against those surrogate models. We found that after a prune ratio of 0.4, the accuracy of the surrogate models drops by a lot, more than 0.6 in most cases, in which case we do not consider them in our analysis. However, between a prune ratio of 0.1 and 0.4, we found that for most datasets, the false negative rates rose rapidly. Thus, we found that pruning actually successfully evades GrOVe. Now, how do we deal with this? In order to make GrOVe more robust, we augment the training data of the similarity classifier. Simply put, we include the outputs of the models with a prune ratio less than equal to 0.4 into the training data of the similarity classifier. And this is because prune ratios after 0.4 have a greater than 10% decrease in accuracy. And this technique of data augmentation can be extended to other evasion techniques as well, which might come up in the future. After training the similarity classifier using the data augmentation technique we just mentioned, we tested GrOVe against those same pruned models. We found that between a 0.1 and 0.4 prune ratio, all of the surrogate models were correctly identified. For other evasion techniques such as fine-tuning, we refer you to the paper. Lastly, we test how efficient GrOVe is in terms of the time it takes to generate the training data for and train the similarity classifier. We find that it is influenced primarily by the dataset size. Co-author is the largest dataset, thus it takes the longest time to train GrOVe for co-author, while ACM is the smallest dataset and thus it takes the least amount of time. However, using a single A100 GPU with 40 gigs of RAM, we find that GrOVe was able to train the similarity classifier in less than 3 hours. Thus, the main takeaways of our work is firstly identifying that model extraction attacks against GNNs are a problem. We found that surrogate models generate similar embeddings to the target model, and we bring about GrOVe, which is effective, non-invasive, robust, and efficient. For more information about the kind of research that we do at the Secure Systems Group, please check out this link. Thank you.